what I want to do, I want to just follow up on what Engel was trying to talk about this Fourier transform in certain cases that they do really exist, and try to show how they reflect with what he says. So I'm going to talk about first gamma functions as Fourier transforms of measures. So I give an example from my own work, and then I'll look at monoids and I'll try to connect them to these things, and then I'll go to the cases of Braverman and Kazhdan, and I'll prove that their Fourier transform can be really obtained by normalization of intertwining operators. So let me take F a local field. I'm assuming characteristic P, characteristic 0. P-adic, right. P-adic. And let me take G a connected reductive group. And let me consider a parabolic subgroup. Mn, I write a Levy decomposition, parabolic. Now let me assume it contains a minimal parabolic, the usual way. So M contains M naught, and N is contained in N naught. And I will assume a maximal torus, maximal split torus, a maximal split torus. In M, I put it in M naught. And then of course I have the Weil group. Group of G and A naught. And of course I like to talk about intertwining operators, so I have to put induced representations. So I'll have a representation sigma irreducible, admissible representation of M of F, and I induce this up to G of F. Just the normal way, the usual way. And then I'll start, just remind you what the intertwining operators are. I'll take an element W in W. I do it a bit differently than usual people do, and have the Levy subgroup shared. I will have the minimal parabolic shared. And then W is in W. I'll assume that if delta is simple roots of A naught, then the Weil group element that I'm choosing will send if M is M theta, if M is generated with a set of simple roots, theta is in delta, then I require that this W sends theta simple roots to simple roots. And then I can define my operator the same way we usually do. I'll just put this to be the usual, and minus is always the opposite. And then you integrate, you take a function f in I of sigma, and you integrate the sigma and W at a function f. It's just integral over, I have to give you NW. NW is, as usual, always N naught intersected with W and N minus W inverse. And then I integrate these over NW of F. The function would be F W inverse of N G dN. So this will give you the intertwining operator. And then let me assume that things are in a good shape. So N bar is just equal to N minus. So the parabolic is self-associated.
I'm confused.
Yes.
W is in W, but not a representative, or you're not taking a representative?
I mean, for the groups, it's not going to matter. But here I'm choosing a representative, of course.
Okay.
I choose in my work, I do it very carefully. It's just the base. I mean, okay. And then P, I'm assuming P is self-associated. This means if N and N bar and N minus are the same, then P is called self-associated. And then we have I'll take W to be W naught, which is the long element. And then, of course, I take representatives as Bill wants it. And then the intertwining operator is going to look like a f at G is just going to be, I'm going to write this element. I do a broad decomposition for this. This would be M and prime, and I write this as an inverse. So M is in M, and prime is in N, and N bar is in N bar. We can do this for almost all N, and then this integral just becomes an integral of sigma of M, F of N1 bar inverse, N bar, and N1 bar dn, and this is a convolution. This is just a convolution. So this is a convolution. This is just sending. Let me define phi to be this measure, sigma of M dn. I'll take phi to be this measure, simple sigma of M dn, and this is just like a distribution. So it's acting on this thing, and this would be phi sending N bar. And 1 bar. And this is clearly a convolution, so this means that I can write this intertwining operator f as a convolution of this measure with f. And to this I can apply Fourier transform. It becomes a product. The Fourier transform of this becomes the gamma functions that come in, and then, as I will explain, these are the ones that show up in this theory that I use using Eisenstein series. So when I have, I'll start with this, and out of this I show that gamma functions can be written as a Fourier transform of this measure. So let me now assume G is quasi-split. And let me assume that I have an additive character, generic character. So now no longer I have to worry about, since it is quasi-split and naught is P naught is a Borel subgroup, and then the generic character of N naught of F, and then I can do the usual thing. I can take the Whittaker functional, so I can take psi of F, which is just an integral over this N naught of F, and then I can also take psi of this measure, which just simply means I will get sigma of M psi of N bar and then dn, and I'll do this over N of F. No longer we have to worry about this. Will be, I'll do it. What?
Yep.
What do you mean? Oh, F is the field. Which one? Oh, function is an induced space. Function is always.
There's no F in your formula.
Yeah, it says no F on psi. Psi of F.
No, this is psi of phi. Oh, I'm doing the Fourier transform of this. Yeah. And then you quickly see that if I take psi of intertwining operator at F, which would be psi of this phi convoluted with F, this is very formal, of course. Fourier transform, so the Whittaker function of the intertwining operator composed gives me this psi of phi, and this psi of phi is the Fourier transform of this measure. And on the other hand, there is this theory of local coefficients, and you know that this is basically the same thing. So this basically says that up to some kernels, this basically says that this Fourier transform of that measure is a product of gamma functions. So this is a product of gamma functions. You can normalize it with this. This is a normalizing factor for intertwining operators. And you can normalize it with this, and the conclusion would be that this normalized Fourier transform is unitary. That you will conclude. This These are normalizing factors. They are not like the ones that Langlands requested, but they are gamma functions. They are basically epsilon L of 1 minus S divided by L of S, a product of such things for different representations. So
by gamma function, you mean a real gamma function?
Gamma function which comes into the functional equation. So it's an epsilon of S and R, and then L of 1 minus S divided by L of S. So that's what?
Little gamma.
Little gamma, yeah, okay. All right. Now, I'm gonna come back to this after I say a few words about monoids. I mean, I'll be benefiting quite a bit from what Go has said about them. And then you will see there is a good connection, even not only in the finite dimensional cases, but in infinite dimensional cases. After that, I will look at the construction of Braverman-Kazhdan and show that these normalizing factors really give you the Fourier transform in the cases that we know. Now, from theory of monoids, I'm just going to say a few words. I mean, he already did say, I'll take K algebraically closed. M is going to be a monoid. So it is an associative. It has an associated product. It is flat. It's an associative, and it is a normal variety. It's a fine variety, and all that. And then, if one is in M, you can talk about G of M to be units in M, and we will say that we will say M is reductive if G of M is reductive. So the similar things that he defined. And the point, I mean, he sort of moved over these things. The point is that you want to fix G prime to be drive group of G, and you want to show that if you fix your G prime, you can produce all the monoids which contain G, for which G prime would be the derived group of G, their units. Now, how do you do this? You do this by abelianization. You take M, you let G prime cross G prime, or I'll just put it G prime act on it on both sides. This will give you an tori variety here, A. I'm just going to write it. This is abelianization. And then you have the map pi from M to A. This is the GIT quotient of M, geometric invariant theoretic quotient of M. And then you build out of this. I mean, if your G prime is fixed, you can out of it build a universal monoid. And this you do by looking at, I should have used that word first. You will look at G prime, T prime maximal torus, Z prime its center. You define a G plus, which is G prime cross D prime divided by Z prime. And then you basically go and you take, I mean, you can embed this G plus in products of Gm to the rank times product over all of GL of Vi or V omega V rho I. Rho i's are fundamental representations. I'm assuming G prime is simply connected. And then you take the closure of this, and then of course you have Ga to the R, and you have product of endomorphisms of V rho I. These are all fundamental weights. And you find the closure here, and that will be denoted by M plus. This is M plus. Now, given a map from your abelianization to the abelianization of this M plus, you can, given a map which I call it phi AB from A to A plus, you can produce a monoid M, which is just a fiber product of this. So you get A cross M plus divided by, over A plus, and this is just all the pairs A and M plus, for which if you look at the image of A is going to be equal to I have the map from A plus to A plus, and this is pi plus, so it gives me a map from there, and I want this to be equal to pi plus of M plus. In this fashion, you produce a monoid which contains a reductive group whose derived is G prime, and all of them are found like this. This is Weinberg's classification of monoids. So you start with a map from A to A plus, and then using that, with that one fixed, you can produce the monoid. Now, this pretty much brings us to trying to build them for every, remember, we were interested in doing this for every representation of the L group. We wanted to produce a monoid. And so let me assume I have this phi AB from A to A plus, and I assume that as I said, and so I found that thing. Now let me assume I have a map from GM to T plus, and T plus is really nothing but T add. It is nothing but T prime divided by Z prime. So I have a map from GM to T plus. So this is a co-root of T plus, which is T add. And out of this, I'll get, of course, a map from T check simply connected, and that's going to be to C star. So this is a character of this T check simply connected. And I may assume that I start with the representation R of the group of the G check. And then representation R has a highest weight, which will be lambda. Highest weight will be lambda, and out of that one, I'll have this map, and then I can, if this map is dominant, then I can really extend it to a map like this, and then out of this, I can get this monoid M lambda attached to lambda. So I can start with a co-character of T plus, which is T add. I'll end up with a character of the dual setting, T check simply connected, and that will be, I'll assume that's highest weight of my representation R. That will give me my M lambda through this construction. Now, if you do these constructions for example, GL2, in fact, if you want to do it for fundamental weights of SL2C, so there is the fundamental weight is delta 1, and then symmetric powers are n delta 1. Then by this definition, your M, the M which corresponds to n delta 1, these things are just going to be pairs of A and plus. Your M plus is just going to be endomorphism of A2, and your map pi plus will be just determinant. This is not true for GL3, just for GL2. And then you're going to have that n delta 1 of A must be equal to the determinant of M plus, or that A to the n is equal to determinant of M plus. So this will be determinant of M2. And if you compute this, you will see that the corresponding group, G in M delta 1, is going to be equal to GL2 if n is odd, and GL1 cross SL2 if n is even. So these are the kind of monoids you have to work with it, and you can quickly compute the group which gives this units. But of course, you have to think of this also as something, and if you want to define the spaces of Schwartz functions, you have to be using this. Now I want to go to the cases when we have any examples that these things are computed and when the Fourier transform is really defined. So these basically go back to the best examples that we have go back to Piotrowski and Rallis, the doubling method. So I'm gonna before I go is that if there is a way of constructing given any finite dimensional representation of a simply connected complex Lie group, you can find an infinite dimensional group which you can put this representation having this as a levy, and then its action on the unipotent radical of n is going to contain that particular representation. The point is that using this construction you can show.
I don't understand.
Yes, I'll explain. If you have a simply connected complex Lie group, G, simply connected semi-simple Lie group G, you can always find the Katz-Moody group G tilde with a Levy subgroup P tilde, which is some L tilde, N tilde, so that if I take the derived group of L is equal to this G. And it can be chosen in such a way that if I fix a rho as a representation, a reducible representation of this G, these are all simply complex groups, then this representation rho appears in the adjoint action of L. In fact, L tilde itself, of course restricted to the simply connected piece, in Lie of N tilde. Just like what happens in the finite dimensional cases, you can always do that. There always exists a complex Katz-Moody group and a Levy inside it with the derived group of that Levy equal to G, so that this representation rho appears in this action of L tilde on Lie of N tilde. You can do that. And you can show that with this construction, that if this is your representation, that you built your thing over, if you compute G lambda, and then G lambda is exactly equal to L tilde. You can show that you start if lambda is the one which gives this representation, lambda highest weight of this rho, then the group which is attached to that is exactly equal to L tilde. You disagree or?
Sorry, okay.
No, but it's true.
Okay.
I,
Believe it or not.
what is bizarre? That you can do this?
No. That you're going to do something with it.
No, that's a different. Locally you can do. There is a periodic theory for these loop groups that you can work with. Globally, we still don't know. But what I have checked these in the finite dimensional cases, they're always true. Then I gave a proof in general, assuming that you will have some local theory. Local theory you can develop for these infinite dimensional groups. And who knows what it goes with this. If you talk to these people, they say that this is a complication we are working on.
See the detail.
What? Yeah. That's what I meant.
What? The theory of Eisenstein's theories, that's the problem.
Yeah, it is the global theory which is the problem.
The spectral proof.
Yeah. Local theory, all I'm saying is that the local theory can be handled. I think that you can develop a theory of local coefficients. At least in the spherical case, you will get exactly the same thing. You take the intertwining operator, you take Whittaker function attached to it, it will give you a local coefficient which would be a ratio of all functions. That's the. But now let me go to the cases that we can do anything about the Fourier coefficients, Fourier transforms.
don't know that the Eisenstein series is analytic from any other point of view. So
What they know, in fact, is very bad because they show that it is entire. I mean, which is not very good.
There's something under this. Well, anyway, let's talk about it.
Okay, there's some that they show that it is entire, which that doesn't help. We know that there are these L functions and they should have poles. But the local theory apparently goes through, works. You can define these intertwining operators, compose them, take functionals, and they give you a ratio of L functions. That's what happens. But let me now go back to the cases that we can do something. So this doubling method. And honestly, this is the only set of cases when the Fourier transform exists, when the gamma functions turn out to be the right one. And the Fourier transform is basically an intertwining operator. It is the just non-normalized intertwining operator doesn't do it. You have to normalize it, and you have to normalize it by gamma functions. Then the resulting thing would be the Fourier transform for that particular problem. So let me start with H is a split group, connected reductive. And P is a parabolic subgroup. Parabolic subgroup. Now, then you take P equal to M U sub P, and then you divide out M by its derived group, and that gives you the abelianization of M. Now, there is, of course, you take XP. This is going to give you the monoid that you want. So XP is equal to H divided by P derived. And we will be really the space of functions that we will apply our Fourier transform to are really come up out of these things. So you will take CC infinities of these XPs. You take all the Qs, all the other parabolics Q, sharing XP, sharing the same levy M, and then you will be really arranging this. You will take some of these things over XQ, and this is going to be you will have some intertwining operator going in here between Q and P. I'll explain all of this. And this becomes your Schwarz functions. This is space of your Schwarz functions. Your basic function is going to be living in here. The cases that you will be getting here are just a generalization, a first generalization of Godin-Jacquet. They will give you all these things will give you standard representations of classical groups. So for standard representations of classical groups, we can define the space of Schwarz, we can define the Fourier transform, and they will give us the right thing. And to get the right factors, you really have to normalize intertwining operators the right way. They will really give you the standard L function. Now, now the first thing, so we're going to look at we'll have XP, which is that quotient. We look at the smooth functions, a compact support on XP, and then we will define these are the operators we define operators P, Q, just like intertwining operators going from CC infinity of XQ to CC infinity of XP. Now these operators are defined by means of, first of all, the non-normalized operators. So I'm going to be now using this paper of Braverman and Kajdan, trying to understand what they're doing. This is on intertwining, normalized intertwining operators. Intertwining operators. and they have these normalized intertwining operators between them. And first of all, there exists they call it RPQ. It's a map from here to here, but this is just like intertwining operators. This is just a standard intertwining operator. So basically, if you look at it, I mean, this is this XP. I mean, if you look at this, this is like smooth of functions on XP. This is basically like induced representation from P of F to G of F from the trivial representation. So therefore, there is intertwining operators between these spaces. You go from here to here. But so in a way, you can produce some functions, but this is not enough. You really have to produce the so-called these other operators that they have. So then this is what I have to define for you. Now they define it in their own geometric way of doing things. They define distributions. They normalize with these distributions. They choose particular ones. They take convolution of all of them. And to each of them, they attach a rational function. What I like to point out, which they didn't, that these rational functions are nothing but normalizing factors of intertwining operators, the ones that we are familiar with. Okay, now let me do that. First of all, the first intertwining operator, they define it in a geometric way, and they just say, I'll take a function f. Well, let's not go to this. Let's go to the normalized one. For the normalized one, they introduce these distributions. They take you as usual. You have a non-trivial character of f check, and then you have then I want to define a distribution. So S is a complex number. You can just define eta psi S to be defined by dx. And dx is the self-dual measure with respect to psi. So this is a distribution on f star. Okay, so they define one on f star. Now then they show that they can attach a Laurent series to this, and they will show eventually they attach to this distribution eta a rational function that they denote by m eta chi of 1. Okay, so this is chi is a character of f star. And you can clearly see that when they do this, all they are really looking at, they are looking at Gauss sums.
You're looking at
Yeah, Gauss sum attached to chi. So basically, this thing is really nothing but chi of x, psi of x, x to the s, this d of x, and over f star. So this is what they attach. So it is basically a gamma function. It's an epsilon times an L1 minus s divided by L of s. Now, of course, this is just on f star. You have to extend it to this to a torus. And I'm just going to do it in the case. They do it in general, but what we need is just our case. What we need is only our case. You will take a torus T. I'm going to take this group, a split torus H that we had. I'm going to look at I'm going to look at M. I'm going to look at all the complex groups attached to them, M check. I'm also going to look at the L group of M abelian check. That would be center of this, center of M check. M was our Levy subgroup. That would be center of M check. And then, then they look at, now of course you have the parabolics P and Q, they contain T. And then you take the, Lie algebra of P. Lie of P, and and then they have the dual, and then they have Q check, and then also they have the U, which will be Lie of UP check. UP check, and then have UP, and then have UQ check. I mean, this is their writing. It's not easy to read them. UQ check. And then they look at the adjoint action of, again, at the adjoint action of this M check on the UP check divided, this Lie algebra is divided by UP check intersection UQ check. So this is the same old story we have. You have the Levy subgroup M check acting on this, and this is of course going to decompose to it's going to decompose to representations of M check, and it will give you characters of this center thing. So let me, this is, and we'll give roots of T check restricted to this center thing. This is just center of M check anyway. This is center of M check. Roots of T check restricted to this is going to give you the, it's going to parameterize this space. It's going to grade this space. So it's going to grade this space. It's going to give all those representations that we usually have. Grade this space. And then they tell you how to compute how to extend this distribution that I just defined at one place by doing this. So let me, if the roots of this restricted to ZM checks are, say, lambda 1, lambda 2, all the way to lambda n, then to each of these, you can make each of these to be characters of your, each of these, each introduces a distribution on F star that you can push back and make them characters on the center of M check, which can be lifted. To distributions on center of M check. And then you tensor these together, and then that gives you the, so then you take these distributions, tensor them, you push them back, you tensor them, convolve them with each other. This becomes a distribution on the center of M check, and then when you take the corresponding rational function M attached to this lambda 1 all the way to lambda n, you're going to end up with a product of these things. And then this product, each of them are really one gamma function for this. So the result, I'm skipping. So let me tell you what they tell us finally. They finally tell us that if you compute this thing, so the proposition that you can try to understand from what they are saying is that if I have this parabolic P and I have M, I look at delta P, the modulus character of P as a representation of M. Okay, then this rational function that they introduce, which comes from this convolution of these distributions, this is exactly the normalizing factor that you want. It is just gamma at delta P to the 1/2 add of M check restricted to that UPQ check. So this means take this representation of your M of F, take this representation of the Levy, adjoint of Levy on that, then you will get this rational function that you want is this. And then their normalized transfer is just correcting your non-standard one with this. Correcting your non-standard one with this, or of PQ. So, and the normalization here, this normalizes. This operator is going to be a normalized operator. The normalization factors are going to be gamma functions. Now, what is the Fourier transform? The Fourier transform is just going to be this thing acting on that space. So that Fourier transform that in these cases that Engo was talking about, the Fourier transform of PQ is just going to be this. So you take the standard intertwining operator PQ, and you multiply it by this normalizing factor, this gamma of delta P add of M check on this UPQ check, our usual normalizing factor. So this basically says that when you start with this space CC infinities of xq, then apply to it this operator. These are functions which are on these are the functions which are in the induced space. You apply this thing to it and then sum it up over all the Q. This would be your Schwartz space, the Schwartz space of XP if you want. And then the Fourier transform is defined exactly by taking the intertwining operator and normalizing this way. Now, this agrees completely with what Piotrowski and Rallis have done. Piotrowski and Rallis have done this doubling method to compute the factors for the standard representation of classical groups. They just take they assume n is equal, n is even. They look at ON or SPN. They define group H by the doubling. So H would be either O to N or SP to N. This is group G, and G cross G embeds in H. Embeds in H. They imitated what Goleman Jacquet did, of course, in their own way. They have this representation. They take P to be Ziegel-Levy. So the one when M is equal to GLN. And then they do induce from P of F to G of F, the character delta P to the S. And then they define the intertwining operator on this. MW naught is the operator for long element. Long element. So this is just A of W naught. And they act on these functions in this space, which is exactly this space CC infinities that we talked about. They define as local zeta integral, just the same way that Goleman and Jacquet did. And they get a proportionality factor of that, and they call it gamma, which is the wrong gamma. So then they define the WF is again in this induced space, and then this is just defined to be integral over G of F of the embed. F is a function in there. They're embedded. They evaluated at G and 1. Remember, there's an embedding of G cross G into H. They go and take a function. Fs is a function in here. They evaluate it in this and integrate it against the matrix coefficient. Pi of G, V, W. And then they do this. So they have exactly the same zeta integral as Jacquet and Goleman have. Then they look at the Fourier transforms from them, not the right one. It's just going to be this equal to this MW naught acting at F, and then again V and W. And then these two things are proportional. So they give you a gamma function. They write it in this is not big gamma. It has nothing to do with the normal gamma function. And then this is Z of F, V and W. Now this is wrong. This is supposed to give you gamma functions for standard L functions, but it is not. It will be that if you multiply by this. So the same normalizing factor that makes this to be the right gamma function is the one that gives you the Fourier transform. So that's the point, and then you multiply. So then when you multiply this would be that f of PQ that Braverman-Kajdan introduced to you. And when you put that factor here times gamma, this becomes gamma function for pi standard representation, Z FVW. So it shows, of course, you have to really understand their paper. It's not an easy paper. I called when Wei Li wrote a paper about these things. And I wrote to him, I said, can you explain to me where did they get these normalizing factors? Does it have to do? And he said that is one of the mysteries of that paper. He said he doesn't understand how they did it, but this is what really happens. So the point is that the normalizing factors are these gamma functions. Gamma functions are, as I said, epsilon s L of 1 minus s divided by L of s. So they are not, Langlands suggested this, which works perfectly when you do work with intertwining operators and trace formula and Eisenstein series and everything. But these guys also normalize operators. And these are the ones which come into this theory that these guys introduced. It is hidden in their paper. You should read that paper. These guys are geometers and physicists, and they are influenced by that. But for me, I'm an automorphic person. I have to understand it in the language of automorphic. And I pressed and pressed, and I realized that's what they do. And I think I'll just stop here. I'm sorry. I'll probably